The universe is vast. It stretches out in all directions, a cosmic ocean of unimaginable size. Within this ocean, our planet Earth is but a tiny island of life, a pale blue dot suspended in a sunbeam. For all of our history, we have gazed up at the night sky and asked a simple yet profound question: are we alone? It is a query that has echoed through the ages, pondered by philosophers, scientists, and dreamers alike. The sheer number of stars in our own Milky Way galaxy, estimated to be in the hundreds of billions, suggests that the odds for life elsewhere should be high. Each of these stars is a potential sun, perhaps warming its own family of planets with the gentle touch of its light. Despite these astronomical numbers, the cosmos remains stubbornly, unnervingly silent. We have spent decades listening, pointing our most sensitive radio telescopes towards the heavens, hoping to catch a stray signal, a whisper from another civilization. This silence is what scientists call the Fermi paradox. If the galaxy is teeming with life, and some of that life is intelligent and technological, then where is everybody? Why haven't we seen evidence of their existence? Or are we, against all statistical probability, the only thinking beings in this immense cosmic arena? This has led some thinkers to propose that perhaps we are looking for the wrong thing. What if, instead of listening for a deliberate message, we should be looking for the unavoidable side effects of a civilization's existence? Just as our own cities glow brightly when viewed from space, a truly advanced alien society would surely leave a much larger, more obvious footprint on its environment. The physicist Freeman Dyson. Born in England in 1923, Dyson was a visionary thinker whose work spanned quantum electrodynamics, solid-state physics, and nuclear engineering. At the Institute for Advanced Study in Princeton, this environment of intense intellectual curiosity encouraged bold, speculative thinking. Dyson approached this problem as a physicist. He considered the physical constraints that any advanced civilization would inevitably face. At the heart of it all, he identified a universal need: energy. To continue growing, they would be forced to harness the only truly abundant energy source available to them, the total output of their host star. In 1960, Dyson published a short but revolutionary paper in the journal Science titled "Search for Artificial Stellar Sources of Infrared Radiation." He suggested that a society capturing its star's power would create a signature that would be visible across interstellar distances, a strange glow in the infrared spectrum. Dyson's original concept was far more elegant and practical. He envisioned what is better described as a Dyson swarm, a vast collection of billions of independent orbiting solar collectors. This swarm could be built gradually over a very long period. Over many generations, the swarm would grow thicker and denser, eventually surrounding the star almost completely. Each of the trillions of individual collectors in the swarm would act like a solar panel, but on an industrial scale, absorbing the intense radiation that would otherwise be lost to space. The energy could be beamed wirelessly from the collectors to where it's needed using focused microwave or laser beams. The key to detecting such a structure lies in a fundamental law of physics, the second law of thermodynamics. There will always be some waste heat. The waste heat would be radiated away at a much lower temperature than the star's surface, meaning it would glow in the infrared part of the spectrum. To conduct this search, astronomers use specialized telescopes that are sensitive to infrared radiation. Space-based observatories like the now-retired Spitzer Space Telescope were perfect for this job. Scientists use computers to cross-reference data from different sky surveys, looking for objects that are unusually bright in the mid-infrared range, but appear dim in visible light surveys. The first and most daunting challenge in searching for a Dyson sphere is the sheer mind-boggling scale of the task. Our Milky Way galaxy contains somewhere between 100 and 400 billion suns. Trying to survey every single one of them for the subtle signs of astroengineering is a monumental undertaking. In 2015, the normally quiet world of astronomy was thrown into a frenzy by a single star. Located nearly 1,500 light-years away in the constellation of Cygnus, Chi-C 846285 would become famous as Tabby's star. The discovery was made by citizen scientists in the Planet Hunters project, volunteers sifting through data from the Kepler Space Telescope. When they looked at the light curve for this star, it looked like nothing they had ever seen before. Instead of tiny dips, it was plummeting, at times losing up to an astonishing 22% of its light. Tabitha Boyajian and her colleagues spent years trying to find a natural explanation. They checked for instrument faults, data processing errors, and every known type of stellar variability. Nothing fit. After years of investigation, the most plausible explanation involves a huge, opaque cloud of circumstellar dust. The key insight came from discovering that the star's light was blocked more effectively at blue wavelengths than at red wavelengths. The story of Tabby's star is a perfect illustration of the scientific process in action, showing how careful observation can slowly peel back the layers of a cosmic mystery. Even if a Dyson sphere exists, we face the immense gulfs of time and space. The light we see from a star 1,500 light-years away is 1,500 years old. We are cosmic archaeologists, sifting through fossilized light. The future of the search relies on developing more sophisticated strategies and smarter AI algorithms to comb through the coming data tsunami from next-generation telescopes. We are on the cusp of a technological revolution in astronomy. The Vera C. Rubin Observatory will create a decade-long movie of the southern sky, capturing the changing brightness of billions of stars. The James Webb Space Telescope, with its incredible sensitivity to infrared light, is the perfect instrument for follow-up investigations of any candidates we discover. Imagine that tomorrow, astronomers announce the confirmation of a Dyson sphere candidate. The immediate impact would be a scientific and cultural earthquake, front-page news on every screen on the planet. It could foster a new sense of global unity, a cosmic perspective that transcends our petty conflicts. Faced with evidence of such an ancient and powerful civilization, our own conflicts might seem trivial. In the end, our search for Dyson spheres is an expression of hope. It is the hope that intelligence is not a fluke, that technology can be a tool for long-term survival, and that the universe is not empty. The silence we have encountered so far is not necessarily evidence of absence. In cosmic terms, we have just opened our eyes and cupped our ear to the keyhole of a vast, unexplored mansion. We are a species of explorers, driven to look over the next hill, across the next ocean, and now towards the next star. The silence of the universe does not deter us. It motivates us. So we will continue to look. We will build bigger telescopes, design smarter searches, and peer deeper into the cosmic darkness. We will sift through the light of billions of suns, hunting for the faintest hint of a shadow, the barest whisper of heat that might betray the handiwork of another mind. We do it because the universe is filled with endless wonders, and the greatest wonder of all might be the discovery that we are not the only ones looking back. The search continues, fueled by the boundless possibility that fills the space between the stars.